In this lecture, we'll speak about how to make uncertainty more interpretable and calibrated. Many models convey uncertainty. First, we'll look at classifiers and how to make their uncertainty more interpretable and calibrated. To start with, one might ask, what is calibration? To clarify this, let's first look at a concrete example. Let's say that a model is perfectly calibrated and predicts a 70% chance of rain, or it has 70% confidence that it will rain. Then when it makes that prediction, and since it's perfectly calibrated, 70% of the time it will rain. Now, if it wasn't perfectly calibrated, perhaps only 20% of the time it will rain. So that would mean its confidence wasn't actually reflecting reality. But when its confidence is reflecting reality, when there's a match between the 70% confidence and the 70% probability or actuality of it raining, then it was calibrated. Let's write this a little more formally. Let y hat be the class prediction confidence for the input x, and let p hat of y hat given x be its associated confidence. So that might be the 70% confidence in it raining. A classifier is said to be perfectly calibrated if, for all y hat, we have the probability that it's correct given the confidence equals the confidence. So the probability of it actually raining, given a 70% confidence of it raining, actually was 70%. That's what it would mean for the classifier at that confidence level to be perfectly calibrated. We just established that if we want the predictive uncertainty to be calibrated, then we want the predictions to match the empirical rates of success. Let's look at another example. Let's say we have predictions for various different people, and let's say that for some of the groups of people, we assigned a 75% confidence. And for that group of people, 3 out of 4 of them were correct and 1 was wrong. Then we have the following equation. 3 out of 4 of the trials were actually true, and 75% was the confidence. So in this example, at this confidence level, the model was again calibrated. Now that we know what calibration is, let's zoom out and describe some of the motivations for calibration. One motivation is that calibrated models can better convey the limits of their competency when they express their uncertainty. So, if a model is indicating that it's highly uncertain and doesn't know how to proceed, then human operators can know when to override the model. Meanwhile, if their uncertainty was highly uninterpretable or was meaningless, that couldn't indicate when humans should override the models. So that's one reason for calibration. Secondly, calibrated probabilities can facilitate rational decision making. So let's say there's a high stakes decision, then having probability estimates that are actually calibrated and represent reality can be quite useful for making a more prudent decision. And calibrated probabilities can be useful for having improved risk estimates. So recall that risk can be written as probabilities multiplied by losses or by impacts. If we have good probability estimates, then we have better risk estimates. Meanwhile, if our uncertainty is less interpretable or more vague, like let's say the uncertainty is, there's a distinct possibility of the event happening, or very likely, or unlikely, we can't get a very good precise risk estimate with that type of vague verbiage. But if we have calibrated probabilities, our risk estimate can reflect reality far better. Next, machine learning subsystems are easier to integrate if each system is well calibrated. So let's say we had some underconfident subsystems and then some overconfident subsystems, and we'd like them to communicate and interface with each other. We'd like to integrate them. Well, probabilities don't have the same meaning between these systems. They're somewhat speaking a different language. Probability in this case is not a common currency, as some probabilities tend to be very high for some models consistently and some very low. They're not reflecting the actual rate at which things happen. So if they're calibrated, then they're having a common currency, and probabilities can be meaningful when they're interfacing with each other. Finally, model confidences are more interpretable the more they are calibrated. Calibrated probabilities have meaning, and that's how they can help humans understand what the probabilities mean. We've seen that there are motivations for calibration, and usually a first step is to try and measure it. But before we try and measure calibration, we need to raise a distinction between calibration and sharpness. Sharpness is about predictions being maximally certain. So the idea is that we don't want predictions that are about 50% very wishy-washy or highly uncertain. We want predictions that are close to 1 or 0. So let's contrast sharpness with calibration. In one figure, we show sharpness, and in another figure, we show calibration. Which is which? The left figure depicts a set of calibrated predictions, but they're not sharp. And at the right, we see sharp predictions, but they're not calibrated. Calibration and sharpness are a part of proper losses. A proper loss, also called a proper scoring rule, says that if a model had to forecast only one probability, it would be the empirical success probability. So the probability that minimizes a proper loss is none other than the empirical success probabilities. No other probabilities minimize that loss. An example of a proper loss is the log loss, which is often used for training classifiers. The Brier score is also a proper loss, which we'll get into in the next slide. But in short, a proper loss function decomposes into a sum of a calibration term and a sharpness term. The Brier score is a possible proper loss. It's the difference between the confidence and an indicator for whether the prediction was correct. And that difference between the two is squared. So consequently, if the prediction was that something would happen with 0% probability, but it actually happened, then it would be 0 minus 1 squared, or 1. Meanwhile, if the prediction was always correct and always 0 or 1, then the Brier score could be minimized. In this example, the empirical success rate is 2/3. Since the Brier score is a proper loss, it's minimized if the prediction probability is 2/3. If the prediction probability was anything else, then the Brier score would not be minimized. If the Brier score's square was an absolute value, would it still be a proper loss? Well, in that case, the minimizing probability would actually be the median, namely 1. So consequently, that wouldn't be the actual empirical success rate. So an absolute value would not be a proper loss. Since the Brier score is a proper scoring rule, or a proper loss, we know that it decomposes into a calibration and sharpness term, or we'll call it here a calibration error and refinement term. When computing the Brier score, it's common to decompose the calibration error and refinement into confidence bins. So we're assuming that we partition the n examples into b bins. Why are we doing this? Well, we want to compute the calibration at different confidence levels. So some examples might have a confidence around 75%, and so we want to see the actual empirical success rate of the examples that had a 75% confidence, and then some other examples might have a much lower confidence, and we want to see its success rate. So we're going to partition these examples into different bins. This might be done in the following way. Let's say we have a bin size of 100. Then we're going to sort all of the n examples by their confidence, and we're going to group the first 100 examples that have the lowest confidence. And then we're going to group the next lowest confidence examples into a bin with 100 examples. So we're then going to look at the probabilities or the empirical success rates of those bins and contrast them with the average confidence in those bins. The calibration and refinement terms are written in this way when they're decomposed into bins. As we can see, there are averages over the members of the bin. In the calibration term, there's an average over the indicator that indicates whether the prediction was accurate or not. And that's being subtracted with the average confidence of the members of that bin. So we're looking at the discrepancy between the empirical success rate and the confidence of the examples in the bin, and then we're going to square that difference for the calibration error. Meanwhile, the refinement term is minimized when its two terms that we're multiplying together are either 0 or 1. That is to say, if the example is, or if the bin examples are always right, or if they're always wrong, then the refinement is minimized. In consequence, the Brier score incentivizes models to be well calibrated through the calibration error term, and if the model is highly accurate, then the refinement is minimized. So Brier score is mixing together calibration notions and accuracy notions. Consequently, we might just want to look at the calibration rather than the refinement term. Consequently, a measure for calibration is the RMS calibration error, which just looks at the calibration error and isn't tangling calibration with accuracy. The RMS calibration error is just that calibration error from before, but then we're taking the square root of it. Some researchers might use absolute values instead of the root mean square, but this doesn't have as good of a theoretical basis because that wouldn't correspond to or be related to a proper scoring rule. A way to visualize the extent to which a model is calibrated or miscalibrated is through a reliability diagram. Let's look at these reliability diagrams. Turning to the left reliability diagram, it corresponds to a less calibrated CFAR 100 classifier. We can look at one of the blue bars, say the bar corresponding to the examples between the 80% to 90% range. So we can look at the accuracy of all the examples with a confidence between 80% and 90%. And what we find with that reliability diagram is that the accuracy is beneath what the confidence would suggest. Consequently, this is showing a overconfident classifier. The right reliability diagram is for a more calibrated classifier. As you can see, there's smaller gaps between the blue bars and the dashed line. If the model was perfectly calibrated, then the outputs would lie along that dashed line. This is a way in which reliability diagrams can capture the overconfidence or underconfidence of various models at different confidence levels. It's worth mentioning that the reliability diagrams in this slide use a uniform binning scheme. Consequently, they put all of the examples in the 90% to 100% range in the same bin. Now, it might be the case that actually the majority of the examples lie in that bin. So that would give us a somewhat coarser estimate between the mismatch of the confidence and the accuracy of many examples. An alternative is to use an adaptive bin size. With an adaptive bin size, we put examples with similar confidence levels in bins of a fixed size. So, for example, if there are fewer lower confidence examples, like say there are 100 examples between 20% and 28%, then they're all put into the same bin size. And if there are 100 examples between 90% and 91%, they're put into a bin. So with an adaptive binning scheme, we can come up with a less coarse estimate of miscalibration. Let's speak about ways to improve calibration. Ensembles are a highly effective, albeit computationally expensive, way to improve calibration. So with ensembles, we're given M models, and what we're doing is we're averaging the softmaxes of the models together and using these combined softmax probabilities to come up with a new confidence estimate. While this just slightly improves accuracy, it more substantially improves calibration. So ensembles are a fairly powerful technique for improving calibration. Another way to improve calibration is by way of temperature tuning. Models can become more calibrated after training by adjusting the softmax temperature. So if we divide the logits by a temperature T, that can change the shape of the softmax distribution. The softmax distribution might get substantially more flat or uniform if T is very large, like say 1000. If T is very small, that is to say near zero, then one of the classes may end up taking the majority of the probability mass, and the softmax is substantially more sharp when the temperature is low. The idea behind softmax temperature tuning is to tune a temperature parameter T so as to maximize the log likelihood on a validation set. This happens after the network has been trained on the training set. So we're given a network, it's already been trained, and now what we'll do is we'll perform inference on the validation set, but try and find the softmax temperature that will maximize that log likelihood on that validation set. Since the log likelihood is a proper scoring rule, this temperature will help us get a more calibrated softmax distribution. I should note that for temperature tuning and for the ensemble method, we're not training with the RMS calibration error loss during train time. The models are trained normally. We're just using the RMS calibration error for evaluating the calibration of models. Here's how various models perform under distribution shift. The figure shows that models are less calibrated under distribution shift. So there's a clean test set, and there are different ImageNet-C corruption severities. We're plotting the average value calibration error, which is similar to the RMS calibration error, but this paper opted to use absolute value due to an unfortunate convention. There are several different models plotted. There's the vanilla model that hasn't had any modifications to it. There's a model that had temperature scaling adjusted to the softmax probabilities after it was trained. And there's an ensemble model which takes many different vanilla models and just averages their softmaxes together. There's some different methods that we didn't discuss in these lectures. As we can see, the vanilla model isn't that calibrated under distribution shift, but some methods, such as ensembles, are particularly calibrated under distribution shift. It's also worth mentioning that since models are less calibrated under distribution shift, it shouldn't be too surprising that they're also less calibrated under adversarial attacks, which try to directly attack the confidences. Let's now move from calibration for classifiers to calibration for numerical regression models. Since we don't have a notion of confidence in a class, we'll need some different objects to calibrate. In this case, we'll want to calibrate intervals, and we'll want to calibrate quantiles. With calibration for classifiers, we wanted an X% confidence matching an X% empirical success rate. The idea for confidence intervals is fairly similar. Here's the setup. Given a question with numerical answer Y, we can ask the model to output an interval with confidence C, such that the true answer falls within the interval with probability C. Here's an example. We have several predicted intervals at different time slices, and most of those capture the actual point. Meanwhile, one of the points falls outside of the interval. So, if this is a 90% confidence interval, then 9 out of 10 of the points were within the confidence interval, and one of them was far outside of it. So, this is an appropriate confidence interval. There's a 90% predicted probability, and that's matching the empirical probability of Y falling into the interval. A data set for confidence intervals is interval QA. It has many numerical estimation questions sourced from various NLP datasets such as Trivia QA and Squad and Math and so on. A motivation is that we want confidence intervals because they offer more insights than just point estimates. And we want models that are calibrated over large numeric ranges. Third, we want to have predictions for large-scale complex word problems, hence the diversity of questions in interval QA. What are some ways to assess the quality of confidence intervals? A basic metric is to look at the length. Generally, shorter confidence intervals are more conservative, and that might be useful. However, that might come at the cost of it being calibrated. So to look at the calibration of confidence intervals, we can use the RMS calibration error, which is not the same as the RMS calibration error from the classification setting, but they're similar in spirit. So the RMS calibration error is a possible metric for measuring the miscalibration of confidence intervals. Let's say confidence levels are indexed by lowercase c. We might want several different confidence levels. So we might have a 50% confidence level, 55%, 60%, and so on from 90% to 95%. For sake of example, let's say that C corresponds to a confidence level of 95%, or script I superscript C is 95%. Then the model is going to output a confidence interval corresponding to that confidence level. It will output that through a lower and upper bound for that example K. Then let's look at the quantity inside the square bracket. We're averaging over all the examples in the bin, and we're looking at whether the answer is within the confidence interval. If C is corresponding to a 95% confidence level, then we want that quantity in the square brackets to be 95%. We'll subtract that from script I superscript C and square the difference. This gives us the RMS calibration error for that confidence level. And then what we can do is we can average over all the confidence levels to get the total RMS calibration error to judge the quality of these confidence intervals. While performing numerical regression, one might want to forecast or predict quantiles or cumulative distribution functions rather than just intervals. Let's say that for an input x, there's a continuous label y. And let's write the CDF f from script y to the interval 0 to 1. Now we can discuss what calibration in this context means. We can take any example whose probability is p. In this example, p equals 90%, and the region associated with that quantile is in green. We say that the model is calibrated if 90% of the labels fall below the 90% quantile, and this should be true for every quantile. Let's talk about improving calibration in this setting. One idea is to recalibrate by learning a mapping between the predicted and empirical probabilities. So here's an example of a model predicting some quantiles. It might say that there's a 60th percent quantile and a 70% quantile and a p quantile. But the data might actually be quite different. The 60th percent quantile actually is more like the 42nd percent quantile, and the 70th might actually be more like the 48th according to the data. So what we can do is we can collect an estimate of what that quantile actually is, and then we can try and learn a mapping from what it said the quantile actually is to the actual data. So that's one way to recalibrate and improve calibration for quantiles.